Derive an expression for the horizontal force on the spherical end cap of a horizontal capsule with cross-sectional radius r that is half filled with fluid. So this is going to be the exact same figure as the last problem. Let's draw it real quick. And this again will have half of it will be filled with fluid. It has a cross-sectional radius of r. Only this time we're finding the sum of the horizontal forces. So since we're finding the sum of the horizontal forces, we gotta set up an integral. That integral would be just use black. That integral will be f of x is equal to the integral d f of x, right? And so since we're trying to find the forces pushing against the cell wall, we're going to use, instead of d f of x, we're going to be using the pressure times that by the area. And the area in this case will be changing depending on where we're taking the depth. So I'm going to draw the figure from a side view. And so we have filled with fluid, has a radius of r, and we are measuring it. We're measuring different points of force, different values of force at whatever depth, and that depth will be h, and we're going to take downwards to be positive, right? So we're taking multiple points of depth, and with that we're going to be finding the area of whatever tiny area at depth h. And so the height of that area will be dh, but we need to find this area right here. We need to find the area of this bottom piece, or the length of that bottom piece, to find the area. So I'm going to draw a figure right here. This is the fluid, and so we're taking measurement of h, so whatever depth we're at, right? So we're at whatever depth h, and so we need to find this bottom piece in order to find dA. So we're at a depth of h, and so to find the bottom area, we can take the radius and extend it to the outer part of the circle. And since this is a right triangle, you can use the Pythagorean theorem to find the length of this side right here, and that would be r squared minus h squared all in the square root. But since that's only for this part and not this part, we're going to need to multiply by 2 so that we can cover both of those lengths. And so dA would be that equation times dH right there. And then for pressure, we would just simplify that, use the basic pressure formula, rho times G times H, and now we can plug in dA using the formula I just said. That would be 2 times the square root of r squared minus h squared, times that by dH, and again that's dA. So to simplify this, or to make life easier, we can use u substitution on the inner part of the square root. And so when we do that, u will just be r squared minus or h squared, not u squared. And since r is a constant, r will cancel out when we derive u. So when we derive u, we will get negative 2h dh. Yeah. So we can plug those values back in. So we get rho gh times this by 2, and then the square root of r squared minus h squared, you could just make that u to the 1/2 power, and dh would be du, all that over negative 2h. With that, we can cancel out some values. The 2's cancel out, and the h's cancel out. We also move some values outside of the integral. So we can move the negative value on the outside of the integral. Well, wait, before we do that, I forgot to mention about the bounds. The bounds in this case, since we're taking measurements of h along the radius, we're taking measurements of h. So we're starting from here. This would technically just be 0. So the first bound would be 0, and then all the way down, if we extend our h all the way down to the bottom, that's just r. So that's how we get our bounds, 0 to r. Those are our bounds. But with that, those bounds will actually change when we rearrange this integral. So because we move that negative sign onto the outside of the integral, we also move rho and g, that the integral will flip and will also change because we're using a new variable. Instead of using h, we're going to be using u, so we have to change the bounds accordingly. And so, hold on, I don't have a lot of room. So when h is at 0, using the u formula, h will equal, or u will equal r squared, and when h is at r, u will be 0. So those are our new bounds right there. These will change. So this would be r squared. So 0 becomes r squared, and r becomes 0. So the bounds change. So then we also have u to the 1/2. I don't know why I keep doing that. U to the 1/2 times that by du. That's our new integral. And now we can actually integrate it. And so the negative sign, with that, I mentioned that it flips, but that flipping occurs now and not, when we change the bounds. The flipping occurs now. So we have rho g, and then we take the integral of this. That would just be 2/3 u 3/2, and then the new bounds would flip. You get that for our bounds, and then plugging in those bounds into our equation, 2/3 times this by, this would be r squared minus 0 squared, all of that to the 3/2 power. And so 0 doesn't do anything, obviously. And then you apply this to r squared, the 2's cancel out, and you are left with the final equation. F of x is equal to 2/3 rho g, all that times r to the 3rd.